Hello and welcome to a video tutorial for the 2008 Electricity and Electromagnetism exam. Question 1. A velocity sorter is an apparatus that can be used to obtain a stream of charged particles, all traveling with the same velocity. The diagram below shows a simplified velocity sorter. A stream of protons is made to pass between the two parallel charged plates. On the diagram above, use arrows to draw the electric field between the plates. So we have a positively charged plate and a negatively charged plate, so there's going to be an electric field between them, and we just need to use electric field lines or arrows to show how the field acts. And in this case it's going to be a uniform field, it's not going to be a radial one, so we're just going to have straight lines traveling like this, from the positive to the negative. They're supposed to be all the same size and evenly spaced. Although it doesn't have to be exactly perfect, but you want them to be about even to show that, because obviously this isn't the only, the field is constant all the way along here, so the arrows are just to represent that it is like that. And then on the sides as well, from the sides of the plates, we're going to have arrows coming in. Like this. On the diagram below, draw the path of the proton in the field. So protons are positively charged, as we see here, and positives obviously repel positives, and negatives attract positives. So what's going to happen is the positively charged proton is going to be attracted to the negative plate, but it's not just going to go in a straight line. It's going to follow, well, it's a bit like projectile motion, where we have the parabola to show the motion. What's basically going to happen is, when it enters the field here, it's going to be drawn to the negatively charged plate by the force of attraction. So it's going to travel like this, or something like that, because it's just like in this situation here, say at the top of a projectile motion parabola, we see that right here the vertical velocity is 0, just as it is here, and the force of gravity is pulling down, and that's what causes this motion here, and the horizontal velocity is constant, which we have to assume is the same case here. So it'll be the second half of the parabola, basically. Explain why the proton follows this path. Well, I kind of just did that, but the positively charged proton will be attracted to the negatively charged plate. Its horizontal speed is constant. Its horizontal speed and the pull of the negative plate is constant. Pull/force of the negatively charged plate is also constant. Therefore, the proton will move in a smooth curve. The proton in a smooth curve. Towards the plate. I'm sorry if my writing's not that clear. I'm trying to make it as large as possible. I don't know how it comes up on the camera. In order for the protons to travel in a straight line, a velocity sorter also has a magnetic field. That makes sense because obviously we saw in the last question that the proton regularly is just going to kind of go like that. So there's a magnetic field in place to keep it traveling in a straight line. So if the proton is traveling through a magnetic field, and electric field, we need to find the direction of the magnetic field that allows it to go in a straight line. So we're going to use there are various different names for it, the right-hand rule or the right-hand slap rule, that kind of thing. And we've got the proton heading in this direction, right? And we've got the pull of the negative plate and the repulsion from the positive plate going down. So if we try and do this in our hands, it's a bit hard for me to show on the video, but let's say that I'll do it inverted. So we've got this going right with my thumb, and then the force going down. So that means that the pull is going to be from my palm here, going like this. So in that case, it's going to be going into the page. So it'll look kind of like that, going into the page. And they give us the option here, into the page. It's a bit hard to see on video. You can try it yourself though. Explain the effect, if any, of the speed of the proton on the size of the electric force and on the side of the magnetic force acting on the proton. Well, if we have a look at our formula sheet, which is here. So we've got electric force here, and magnetic force here, and here as well. But so if we look at the electric force first, we see that force is equal to EQ, and obviously velocity isn't either of those. Velocity doesn't have an impact on it. We have that E is equal to voltage over distance, but that's not velocity then, so we can't, and obviously Q is charge, so we can't say that the voltage has anything to do with the electric force, which makes a lot of sense as well, especially since the topic is static electricity with no movement. So the force being experienced by a particle in an electric field doesn't change whether it's moving or not, it's constant. The velocity isn't a factor at all. But if we look at the magnetic velocity here, we've got force equals BQV, where B is the force of the magnetic field, just like E is the force of the electric field. And Q is charge, but we do have velocity here. Remember, with electricity, big V is voltage, and small v is velocity. So the force of a magnetic field, or experienced by a particle in a magnetic field, will be changed proportionally, or is proportional to the velocity. I think I'll avoid just writing all that down because I'll just be repeating what I said. So if the voltage between the plates is 220 volts, and the plates are 5 centimeters apart, we need to calculate the size of the electric force on the proton, and they give us the charge as well. Well, I'll go back to the formula sheet again. Well, first of all, let's have a look at this. So we need to find the electric force, so we need to find F. We have here that F is equal to EQ, but we don't have E. But we do have the voltage, which is 220 volts, and the distance of 5 centimeters. So we can substitute this in. So we end up with F is equal to V over D. That's not a very good D. Times Q. So let's do that. F is equal to V over D times Q. That looks like a 9, but anyway. 220, and remember, this is 5 centimeters, this isn't 5 meters, so this is going to be 0.05. 0.5 would be 50 centimeters, so 0.05 is 5 meters. 5, and the charge is this number here, times 1.60 times 10 to the negative 19. Right, so this is going to be, divided by 0.05. Times 1.6 negative 19. Right, so that's equal to, we have to give it to the right number of significant figures, which is going to be 2 in this case, as they gave it to, the lowest we have is 2 for the distance. So this is equal to, I keep forgetting. Okay, so that's 7 times 10 to the negative 16. Oh, 7 times 0, oops. I mean 7.0 times 10 to the negative 6. Yeah, newtons. Right. 3.5 times 10 to the 15 protons enter the field in 10 seconds. Okay, so they're giving us the number of protons and the time. And we also have the charge of a proton here, and we need to work out the current. So let's go back to our formula sheet again. So we need to find the current, I, and we have time, and we have the number of protons and the charge. So that's all we need to use. I is equal to Q over T. I is equal to 3.5 times 10 to the 15. All of that times the charge, which is 1.6 times 10 to the negative 19. All over the time, which is 10. So this is going to be equal to 15 times 1.6 to the 19th. Okay, and this is divided by 10, so that's just going to put that up to negative 5. Or 10 to the negative 5 for the last bit. So this is going to be 5.6. Times 10 to the negative 5. Amps. Because current is measured in amps. I think that's it. And that's the end of question 1, so I'll complete question 2 in the next video, and I'll see you soon.